Pointer. Okay, so good afternoon or good morning, good evening, like depending where you are. So I want to talk a little bit about, as it's written, about kinetic simulation versus in situ measurement. This work is done in collaboration with all these people. So, like first of all, here I want to talk about non-relativistic shocks. It means that the shock propagation is much lower than the speed of light, and I'm focusing on high Mach number cases, meaning that the both sonic and galvanic Mach numbers are way above 10. And these shocks can be found in supernova remnants when supernova explodes and the matter interacts with the interstellar medium. It forms the nice really beautiful objects in our galaxy, and actually these shocks are responsible for the production of the main part of the cosmic rays in our galaxy. And these shocks also luckily can be found in our solar system. For example, Saturn bow shock, also like Jupiter or Neptunian bow shocks. Sometimes even Earth bow shock can exhibit like high Mach number properties. So that's why it's important to look at the properties of these shocks, and these shocks are important in both in astrophysical and in planetary sense. So and here I want to talk a little bit about magnetic field amplification of the shock in these shocks and the electron heating. And why these two things? Because again, these two things have been measured in situ for the Saturn bow shock by the Cassini mission. So like a few words about physics of these shocks. First of all, these high Mach number shocks are supercritical. It means that the upstream kinetic energy cannot dissipate it via Joule heat, and the portion of the ions are reflected back upstream. And actually interaction of these shock reflected ions with the upstream plasma produce different instabilities, forming this well-known for the shocks well-known structure, which consists of the upstream region with the undisturbed plasma, foot region where this ion generation happens, the rump region where ions are reflected. We have overshoot with the maximal density, overshoot, undershoot structures are associated with this ion ring relaxation further in the downstream, and the downstream region with the thermalized plasma. But if we look at some details, the shock looks way more complicated. Because as I said, interaction of these shock reflected ions with the upstream plasma produce various instabilities depending on the shock parameters. And we have as a shock fruit, we have Bohdan instability, which is electrostatic type instability, which heats and accelerates electrons. Deeper in the shock, we have Weibel instability, which presented by these dense filaments. Later on, it can develop into magnetic reconnection, producing very turbulent rump overshoot region. So to obtain such a nice figure and to cover all this physics, we use so-called particle in cell simulations, which is ab initio method, which treats both ions and electrons as particles. It means that we can cover both ion and electron physics and as precise as it's possible, essentially. So when in this method, the field is defined on a grid while particles can have any arbitrary position. So when during a cycle, within this like one-time step, it's done in such a way that we move particles under Lorentz force. Then we can calculate which currents are produced by this particle motion on this grid, and then solve on a grid electromagnetic field equation, Maxwell equations. And then we interpolate back electromagnetic field from the position of the grid to the particles. And then repeat this loop again and again. We can calculate like whatever you have in your plasma simulations. But there is a big trouble with this simulation, because if we compare the simulation parameters with the parameters of the Saturn bow shock, where Cassini measured quite a lot of things, we see that the Mach numbers are sort of the same. Plasma beta, which is a ratio of the thermal and magnetic energy and the shock upstream, is also the same, but we have a trouble with the shock velocity itself, which is kind of 100 times larger and is close to relativistic. And ion to electron mass ratio is also non-relativistic. And it is done just to make this simulation affordable and feasible with modern supercomputers. Because this simulation done on superclusters, and it's difficult to run something with parameters which are more realistic. It means, and like the main idea behind this work is how we can use simulation with unrealistic parameters and understand how plasma behaves in real systems. So we want to understand all the physical processes and what is the scaling of these processes with the shock velocity, how it scales with the shock velocity and the ion to electron mass ratio. So, and the first part is the magnetic field amplification, which was published in PRL just a couple of months ago. So, what do we know about magnetic field in this high Mach number shocks? So, from the work done by five years ago by Ali Suleiman, we have this correlation between Mach number and the maximal measured magnetic field inside the shock. And we have an old model constrained by Leroy for the perpendicular shocks showing this scaling. But we see that it's diverging at some point, but it's not the worst thing because essentially this model is based on a plasma compression and misses a lot of things. At the same time, we know from like 3D peak simulation, from in situ measurements for the Earth-bow shock, from the laboratory experiments, we know that these shocks are mediated by viable instability, which I mentioned at the beginning of my talk. And looking at the simulation data, we see that the profiles for the density and for magnetic field are diverging. Essentially, you create much more field compared to the compression. And if you look at the properties of this magnetic field, like if you split it into Cartesian components and look which components are amplified, you see that you amplify X and Z component, which are associated with the Weibel instability, meaning the Weibel instability is responsible for some magnetic field amplification, which is not expected due to compression. So, and if we look at the trends, so how this magnetic field depends on the Mach number, we see that it's growing, and we can describe it with pretty simple formula. But more important thing behind all these dots, red and blue dots shown here, that we have dots in groups representing cases with different ion to electron mass ratio and different plasma beta, meaning that the plasma beta and mass ratio doesn't play important role for the magnetic field amplification. So it means that in this extent we can approximate our result to the realistic mass ratio case. But there is one more question: what about shock velocity? Because as I mentioned, we have a shock velocity which is 100 times larger than a realistic one. So, and we can go into theoretical plasma physics branch and solve dispersion relation for the Weibel instability, calculate the gross rate for this instability. And once you normalize the gross rate to its natural units, you see that it's proportional to the shock velocity. But what's interesting that dynamic of these shocks is defined by the ion gyro time. So when essentially this value demonstrates how many gross rates for the Weibel instability you have inside the shock. It means that this value only depends on the Mach number. It does not depend on the shock velocity. Meaning that we can take results of our simulation and directly apply and directly compare it with the in situ measurements. Because shock velocity doesn't play any role, mass ratio doesn't play any role, and plasma beta also doesn't play any role. Meaning that we can go like directly to the comparison of our simulations and in situ measurements. And we see that our dots exactly covers the range of the measurements we have. So when doing that, we present like a new mechanism, how exactly magnetic field can be amplified in these shocks, and we show that big simulations can reproduce it really well. Like going to the second part about electron heating, I just show a short version because like longer version you can find in a paper, and it would be like too complicated and too long to present here. But I just briefly explain what's the main idea here. So we know that you never achieve actually in the post-shock region, you never achieve the equilibration, thermal equilibration between electrons and ions. That is confirmed both by simulations and observations as well. And we always see that like some part, like 10–20% of the upstream ion kinetic energy goes to the electrons. So what we can do if we imagine that we have different processes responsible for electron heating inside the shock, you can split this final energy into the sum of energy budgets from individual processes. And essentially modeling is done in three stages. So you need to find all the heating processes. So for this, you need to know like what's the shock structure, like how individual particles behave and how like group of particles behave. Then you need to determine scaling processes. So how efficiency of each particular process depends on the Mach number, mass ratio, shock velocity, plasma beta, like whatever parameter you can imagine. And then you can just match this thing you have with the energy budget you observe in your simulation and calculate this numerical term. So, and first of all, we found 5 heating processes responsible for the electron heating. This is a shock surfing acceleration by the Bohdan instability. So here in the shock front, we have electrostatic instability, which can accelerate electrons by doing trapping of electrons, or it can heat electrons just doing some scattering. Then you have a shock potential, which reflects ions back. I mentioned it at the beginning, but at the same time, it can heat electrons. Then you have magnetic reconnection, which is always associated with the particle heating and particle acceleration. And taking into account that we have strongly turbulent region, shock ramp and overshoot region, particles can be heated due to like random interaction with the magnetic scattering centers. And of course, we need to account for the adiabatic heating. And combining all these things together and then omitting all this boring thing, we can go directly to the result. And the red line represents our heating model with already applied realistic parameters, so realistic shock velocities and realistic mass ratios, and so on and so forth. Unfortunately, like from the in situ measurement for this range of parameters, so high Mach number and quasi-perpendicular shocks, we have only 6 points represented by these green dots. But we see that overall, like taking into account all the assumptions done for these calculations for the in situ measurement and for the modeling, we see the pretty good fit between the model we have and in situ measurement. So, and essentially, like going to the conclusions, it's essentially both these matches between simulations and in situ measurements, both for temperature ratio and for the magnetic field, shows the power of this method, this combination of the peak simulations, which can treat a plasma as basically as it possible, then in combination with theoretical plasma physics, where you solve dispersion relations for different instabilities and data analysis, particle tracing, and all these things combined together, it gives very powerful instrument for understanding how real plasma behaves and how you can explain in situ measurements. And just to be noted that both this temperature ratio and magnetic field inside the shock is very important for diffusive shock acceleration, for the cosmic ray production, and for the production of energetic particles and and the Earth's vicinity, or by the bow shocks of some other planets. Yeah, thank you for your attention.
Thank you, Dr. Artem, for your wonderful presentation. Yeah, I'll leave some time here. If anyone of you have any questions or comments, you can
Yeah,
now
yeah.
go ahead.
Yes, I want to ask one
Yes.
question.
Yeah, sure.
Yeah. Number one, how does Wavell instability amplify magnetic field, and what is the percentage of amplification?
Essentially, if you look at there's this ratio between the average magnetic field inside the shock divided by initial magnetic field, you see that it goes up to 20 to 25. You say if you calculate this delta B over B, like average inside the shock region, it's always about 1. So it's strong fluctuations of magnetic field. So when mechanism amplification, I would say that there are still debates how exactly it's done, but in principle, okay. If I have a tool, so initially you have straight magnetic field line in the shock upstream. And going deeper into the shock, you curve this magnetic field line and you add additional this X component and Z component out of plane compared to your simulation plane. So, but like specific mechanism behind this thing is still debatable. So, and I think it will be published probably within a year or so by one of my collaborators, something new about it, if you're interested.